I'm Matt Burns. I lead the technical marketing efforts at Samtec. I'm also a member of the marketing working group within PCI-SIG. In our video today, we're going to be talking about how PCIe technologies influence embedded computing. A question that arises with embedded computing is how does it differ from general compute? It's very simple, straightforward answer. General compute is a good example of that is our laptop or our desktop or another device that handles everyday functions. Word processing, spreadsheets, email, etc. It uses an x86 architecture, very CPU-based. Again, a product architecture that many people are familiar with for decades, hasn't changed much. Obviously, it's gotten faster, more complexity, etc., etc. But that's general compute. Embedded computing is typically a reduced function set of a general compute solution that targets a specific application. It generally uses different architectures. It could be an ARM-based solution, it could be an FPGA-based solution, a CPU-based solution, etc., etc. Good examples of embedded computing applications can include industrial, like process automation, factory automation, robotics, maybe a medical device, or anything that's specialized computing, single function device, really sets it apart from general computing, which can handle multiple tasks. So we talked earlier about what embedded computing applications include. And when you think about some of those solutions, they've been available and on the market for decades. PCIe technology has been integral into embedded computing applications for similar functions compared to general compute. I/O expansion, linking between multiple root complexes using transparent or non-transparent bridging, multiple endpoints, and the like. Today's embedded systems take advantage of several features that are featured in each successive version of PCIe technology. Backwards compatibility, scalability, low power. A good example of a embedded computing form factor application that leverages PCIe technology is COM-Express solutions. COM-Express is an embedded board form factor that's defined by PCMIG, another industry standards body that works very collaboratively with PCI-SIG. COM-Express modules really are the workhorse of embedded computing. There's various types, various sizes, but integral to that is the fact that they use PCIe technology to go between the compute engine and the I/O. When COM-E modules were first conceptualized 15 to 20 years ago, the leading PCIe technology was PCI 3.0, which gives us a data rate of about 8 gigabit per second, 8 gigatransfers per second. As COM-E and as compute engines for embedded have evolved, there's a necessity to support higher data rates. So PCIe morphed into PCI 4e, and to where we're at with PCI 7. For COM-E applications, the max data rate that you can get is PCI 4 because of the limitations of the interconnect. However, COM-E is still very popular and will still continue to be a workforce within embedded applications because of the fact of several features of PCIe technology: backwards compatibility, scalable, flexible, as well as low power. One of the concerns with embedded computing is the fact that systems have to be future-proof. Form factors don't change as frequently as we see within general compute or within enterprise applications. That allows OEMs that use embedded computing form factors like PCMIG COM-E to leverage their investments over longer life cycles. The fact that PCI Express technology can support backwards compatibility, low power modes, scalability, is integral to its performance or the contributions it makes to embedded computing applications. Something else that's also vital for embedded computing applications is the fact that there's usually expanded environmental variables. So, commercial temp device may be 0 to 70, but if I'm sitting on a factory floor, I may have to support minus 40 to 85 degrees C. So that can be a challenge also in terms of the chipsets that are available to support those applications. However, even though embedded computing solutions don't change very frequently, there is still a need to keep up with the advances in PCIe technologies. Embedded computing applications continue to evolve to respond to market needs. A good example is AI. We've seen a ton of disruption across the entire ecosystem with AI over the last 3 to 5 years. ChatGPT was really an inflection point. And obviously that affects data center, but the same AI capabilities, enterprises, OEMs, researchers are looking how to implement AI at the edge. Another term for that may be the intelligent edge, IoT, all semi-related. To enable that high-level performance in an intelligent edge device requires increased computing power. But you still need to have the environmental variables, the small form factors, the scalability, the flexibility, the ability to have long lead times for industrial applications. That's where embedded computing, leveraging PCIe technologies, really can make a difference. A good example of how PCIe technology, the evolution of PCIe technology, is influencing embedded computing is looking at where COM-E has come from and where it's gone to. We mentioned earlier that it's limited to PCI-4 just due to the infrastructure of the form factor. So PCMIG, realizing that and seeing the need for advanced speeds, looking at the innovation and continued progression of PCIe technologies, has followed up COM-E on the new COM-HPC standard, which is really targeted at the intelligent edge, AI/ML, inference learning, et cetera, et cetera. Why was that necessary? Well, the new COM-HPC standard from PCMIG allows for migration from PCI-3, PCI-4 at COM-E up to PCI-5 and PCI-6 at COM-HPC. So not only is that allowing for increased compute performance with the variety of compute engines that are available, but also higher speeds at the endpoint for I/O, tying things together, and the like. To learn more about PCIe technology and embedded applications, not only now, but into the future, please visit PCI-SIG.com.